Grade 10s, we are going to continue on today with forming compounds. In our last video, we talked about atoms could gain or lose electrons to complete their outer shell. And that we mentioned that they tended to gain and lose electrons to each other. And that's one of the ways that they can complete their outer shell is by trading around those valence electrons. We're going to start by looking at ionic bonding, and then we're going to, in a future video, take a look at how they could also share electrons. So atoms always want to try to get a complete outer shell, a completed valence shell, so they could look like a noble gas. And the reason they do that is that's because that's how they're the most stable. It's kind of like a ball rolling to the bottom of the hill. It will always do that because then it's the most stable. It can't move anymore. So atoms will lose electrons or give them to another element. They'll be a cation. They'll be positively charged. They could gain them from some other element. They are now an anion and are negatively charged. And when that happens, we have ionic bonds. So ionic bonds happen because we have a give and take of electrons. If we have a covalent bond, they share them. Like I said, we'll talk about that in a future video. But today I want to talk about ionic bonds. In this little cartoon, we see that this first atom-type person has 7 valence electrons and needs 1 more to complete its outer shell. And this one only has 1. If he gives it over, this guy now has a full outer shell. It is negatively charged, hence the sad little face. And this element now has given away a negative and is positively charged and is feeling quite good about the situation. But we learned in grade 9, opposites attract. So now these two atoms will be stuck together. So ionic bonds form between cations and anions. The cation, again, is the positive half. The anion is the negative half, and they get stuck together. So a good example is table salt. Sodium, like all metals, likes to give away an electron, and chlorine needs one. And so sodium becomes a positive cation. We call it sodium ion. Chlorine becomes a negative anion, and we call it chloride ion. And the two of them will stick together to form sodium chloride. Call that table salt. Now this worked out quite nice because sodium had 1 to give away and chlorine had 1 to take, but it isn't always quite that perfect. When we name these compounds formed by ionic bonds, the middle half, the part that gave away its electrons, the part that formed a cation, gets to keep his own name. The anion half, the non-metal part, the part that gained the electron, has its name changed to ide. And then we just put the two words together, like sodium chloride. And it's neat because if we put them in water, they'll separate right back out again and float around as separate ions in the water. So before we can go and figure out how atoms are going to give and take their electrons, especially if they don't have the same amount of electrons, I want to take a minute and do a quick practice. And I want to do that quick practice on, do atoms like to gain or lose electrons, just like we had done in the past lesson. So sodium, for example, in group 1 has 1 valence electron. We know all metals lose them, so we're going to lose that 1 outer electron and get a +1 charge. Chlorine, being group 7, will have 7 valence electrons. It gains 1 more to fill up that outer shell and has a -1 charge. Take a moment and pause your video here. See if you can figure out the charges on the remaining elements on this page. Pause your video now and try that. Okay, so we've taken a moment here to show you what the answers are. Beryllium in group 2 loses 2 electrons to get a +2 charge. Fluorine in group 7 gains 1 and gets a -1 charge. Lithium +1, oxygen -2. Potassium +1, magnesium +2. And phosphorus in group 5 has to gain 3 electrons and get a charge of -3. So let's use what we know about this to see if we can figure out how atoms gain and lose electrons to each other to form bonds. Let's start with sodium and chlorine. We're going to use red ink to show you what's going on for the valence electrons in the metal. Since sodium is our metal, I'll put the symbol Na for sodium, and I know it's in group 1, it has 1 valence electron. It says to use blue or black for the nonmetals. Chlorine is my nonmetal, and we figured out on the last screen that it's going to need 7 valence electrons. So here's my 7, working my way around the clock. Now, we know metals like to give their electrons, and nonmetals like to take them. So sodium has 1 to give away, and chlorine has room for 1 more. So sodium's going to give the 1 electron away to chlorine. Now sodium is happy. It has lost all of his electrons. Chlorine is happy. It has gained all of his electrons. In order to make both halves of this compound happy, we needed 1 sodium and 1 chlorine. In chemistry, we don't tend to write the number 1. Chemists are notoriously lazy. So we're just going to simplify this to NaCl, remembering to put capital letters for the first letter in an element name and lowercase for the second. And this compound would be called sodium chloride. So we have figured out the valence electrons and figured out how many electrons we'll have to give and take in order to make everyone happy. Let's try this one with potassium and iodine. Again, potassium is in group 1 on the periodic table and has 1 valence electron. Iodine is in group 7 on the periodic table, and just like chlorine, will have 7. Potassium has 1 to give away, and iodine has space for 1. Remember, everybody wants to eventually have either an empty ring or a full ring. So potassium's happy because his ring is now empty. Iodine's happy because his ring is now full. In order to make this, we needed 1 potassium and 1 iodine, and remember, we don't write the number 1s in chemistry. This is the formula for potassium iodide. Remembering that these names end in IDE, potassium iodide. Let's try this one. In this case, we have magnesium, Mg, and magnesium is in group 2 on the periodic table. He has 2 valence electrons. Oxygen is in group 6. 2, 3, 4, 5, 6 valence electrons. I can see that magnesium has 2 electrons to give away. My metals are always the givers. And oxygen has room for 2. My nonmetals are always my takers. So magnesium has 1 electron to give here and can give another 1 here. At this point, magnesium is empty. He has given away all of his electrons, so he's happy. Oxygen has filled up his ring, so he's happy. Again, even though we had different charges, we needed 1 magnesium and 1 oxygen to make both of them happy. And we still name this the same. It's still magnesium oxide. First name ends in "ide." What do we do in a case like calcium and chlorine? Calcium, just like magnesium, has 2 valence electrons. Chlorine, we've already seen, because it's in group 7 on the periodic table, has 7. Calcium's still a giver. He's got 2 electrons to give away. He can give 1 of the electrons here, but chlorine doesn't have any space to take any more electrons. And calcium still has more to give away. So although chlorine's happy, calcium most certainly is not. So what do we do? The answer is we need another taker. We're going to need another chlorine. So I've drawn another chlorine here, and I can give this electron to this spot. So now calcium's given away 2 electrons, 1 to each of 2 different chlorine atoms. Calcium's happy because his outer ring is empty. Both of those chlorines are happy because their outer rings are full. We needed 1 calcium atom and we needed 2 of the chlorines in order to make this molecule. Again, we don't write the number 1, so CaCl2. Now, even though we have different numbers in this bottom subscript position, we still call this calcium chloride. There's no prefixes or numbers in these names. For ionic compounds, it's simply always named first name, last name. So at this point, I want to remind you about 4 corners around an atom. I'm going to use the symbol X to represent any atom on the periodic table. I picked X because there is no element X on the periodic table. Now I know you're looking, there's an Xe, but there's no just plain X. But to a chemist, the 4 corners around an element mean something. This upper right-hand corner is where we're going to write our charge. It tells us whether we've got +1 or -2. This bottom corner on the right-hand side is where we write how many. So for example, in the formula calcium chloride that we just did, this little 2 was written in the bottom corner of chlorine to mean that there was 2 chlorines. On the other side of an atom, those positions mean something too, even though we haven't been using them. The upper corner is where we write our atomic mass, and the bottom corner is where you would write your atomic number. And we use these when we're doing isotope symbols. Now, isotopes don't change the formulas we have for ionic or covalent compounds, but I just wanted to reinforce to you that where you write numbers around an element matter because they have a meaning to a chemist. So now that we've done some examples, do the rest of the assignment to practice figuring out the formulas and the names of ionic bonds.